yeah, I would like to thank my collaborators. So Yuan was my graduate student who did most of the experimental work here. And then, so part of the experimental work was actually done in Dirk Vandermeer's group. They measured Raman, so we'll be talking about Raman scattering. They measured it in the different systems, which was of a different experimental setup where they could go to the lowest temperature without any polarization sensitivity. But that was also valuable also because the spectra which we saw first were so weird that it was actually nice to have a confirmation that it's all true. So I was happy to work with different theory groups in it, and Natalia and her student were interpreting magnetic spectra, and Pregnant Nicholas was working on electronic spectra, which we obtained. And there are these, so neodymium iridate came from Satoru Nakasuchi group, and then Stephen Wilson supplied us neodymium circonate, which is very nice comparison if you want to look at crystal field excitations. And it's interesting in its own, but it's like our future studies. So this kind of just why we started to do this material and what it's about, right? So there's this parafluors. It's a frustrated 3D structure, and so far they actually were not touched in this conference, even though I know that there are like half of the audience are experts on parafluors. So this particular iridium, so people in frustrated magnets community, of course, are most interested in insulating materials. Iridates are very interesting also from the point of view of electronic band structure. So this is kind of a phase diagram where it describes the interest, which I would say it's kind of a little somewhat outdated. So there is, right, so the A is rare earth, B is iridium site, and there was this phase diagram which shows that it's actually a semi-metal, with, like at that point it was not metal. Now I think the consensus is semi-metal with some interesting topological band which could appear in what was kind of at first recognized as insulating state. Neodymium iridate is the most interesting material in a way that it actually it does have some magnetic transition at 33K and another one later. So neodymium iridate was the most interesting in this phase diagram from the point of view of topological states. So what are about topological states, why we studied it? So the suggestion was that in parafluor iridates there is a topologically protected in metallic state or semi-metallic state. I would say there's topologically protected quadratic band touching at the gamma point, and when time reversal symmetry is broken due to ordering of iridium, then this band structure would split into one node. So there is a very nice paper from Brazil which predicts this, and that's what actually we were looking at to try to prove when we started to work on this material. And I will touch on what we saw in the electronic spectrum as well. But it ended up to be a very interesting and very challenging frustrated magnet, because of in contrast, I think, to all other iridates, we have not only magnetic sublattice and magnetic ordering in iridium sublattice, but we also have neodymium sublattice, which is magnetic and which eventually, as people saw, orders. So we have two interpenetrating frustrated sublattices of this tetrahedra. And so iridium has effective moment 1/2, and then neodymium has very large effective moment 9/2. The iridium has extended orbitals, and so all the electronic structure next to around the Fermi surface is formed by iridium orbitals, and then neodymium is a very localized, has right, so it's 4f, has very localized orbitals. So there is kind of, when we stepped in, there was tons of work done on this material, but we found somehow kind of another like more interesting stuff. So it was known already that iridium undergoes all in, all out ordering N33K, and then neodymium has this crossover into all in, all out state below 15K. So yeah, okay. So one thing here is that iridium is very strong absorbent of neutrons. So neutron scattering, like half of the talks, experimental talks here are on neutron scattering, and I think why there was this space for us to do a lot of stuff here is that neutron scattering is very challenging in the system due to absorbance of neutrons. So actually the ground state was known because of neutron scattering at very low temperatures at 2K, where people look at the neodymium sublattice and then deduct what's going on with iridium sublattice looking at magnetic moment. But actually, like probing iridium sublattice directly, this is a challenge. So, oops. Okay. So it is kind of, it will be a lot of experimental data, and I wanted again like to say that it's basically an everything material. That what we observe here, we observed the spectra, Raman spectra, which consequence of very strong spin-orbit coupling. We know that there are strong electron interactions with materials. We are looking for magnetic wall semi-metal, but we also observe two interpenetrating magnetic sublattices, and with both of them are ordering at low temperatures, and this is something which is main result of our work. We found some excitations which so far we can only explain in this exotic quantum spin-ice fluctuation of neodymium sublattice in the intermediate temperatures. So we using Raman scattering, right? So it's a two-phase process. It's inelastic light scattering. There is a single frequency of the laser goes in, and we looked at the scattered light, and this is a nice figure for the review on mostly focused on cuprate superconductors, which demonstrates the power of this method. So in one shot, we can measure very different, kind of basically probe all the degrees of freedom of the system. We get phonons, gamma fluorescent phonons. We get some magnetic scattering who cooperates it was to Magnum, and we get electronic transition. So it could be interband, it could be intraband transition. It is kind of one of the things which I found that it's very important is because we kind of, with these new materials, there are a lot of sometimes inconsistencies from different measurements, and it comes from some things like disorder, right? So here we can, in one shot, in one spectrum, we can probe lattice, magnetic excitation, and electronic excitation, which also helps to disentangle things like quality of the samples. We will be here. So we were measuring this beautiful crystal of neodymium iridate, which is about 1 millimeter in size. And we can go down to very low frequencies, and that's again a consequences of the fact that, in contrast to terahertz, our diffraction limit is defined not by the size of the crystal, so because our excitation, we actually technically measuring visible light, so we can measure very low frequency excitations at for very small crystals. So we also have a tool-less polarization dependence. So for neodymium iridate, we were working on 111 cleaved surface, and we can measure when excitation and Raman light are parallel or perpendicular to each other. And we can, so in this geometry, we could separate A1G symmetry of excitations from EG and 2G. which actually ended up to be very useful for our work. And so again, like the spectrum will be very rich. We observe phonons, so phonons are easy to interpret. DFT calculations were done for praseodymium zirconate and praseodymium iridate, and those are all Raman active oxygen phonons, both phonons of praseodymium and of iridium, and Raman not active. And so this was easy to interpret, and then our focus and in understanding of the data was in other features which crystal field excitation and magnons of various origin. Okay, so what do we know about this material? We know that it actually has two two transitions. One is at 33K, which was, okay, this is still kind of sub-leftovers to previous interpretation, so it's iridium ordering, and then and so it can be pretty sharp in specific heat, and there is also neodymium ordering, which is observed below 14K, and it's a very, very broad crossover, which already by the time we started, there was an understanding that this is a pretty high temperature, so basically neodymium moments order in the field of iridium moments, which are ordered all in, all out. So that's something that electronic structure is changed by the magnetic ordering was even from the conductivity data, which were published in the work with Dick Vanderwaal and Peter Armitage. And that's, now we go to our experimental data. So we measure Raman scattering in two polarizations as a function of temperature. And here, so these spectra are shifted along y-axis, along intensity axis for convenience, and this one is not. So here we have additional A1G excitations which are visible in the spectra compared to this one. So first we see that it's very complex spectra, and these are phonons. So we can interpret phonons, and phonons also have their own temperature dependence, which I will discuss at the end. And first, so what we will discuss, we'll be discussing all this number of excitations which appear below the temperature of iridium ordering, and then some of them just stay at their frequencies, and this is A1G excitation, right? So it's not present in other polarization, which has actually very, very strong temperature dependence. So here, so again, like kind of what when we are, right, so our interpretation is model dependent. So we look at the excitations which appear below the temperature of the transition of all in what was kind of expected to be all in, all out order of iridium. And then we say, okay, that could be magnetic excitation. This excitation behaves very strong temperature dependence, and so this was our second stage of interpretation. So then we talked to Natasha and asked if she can calculate Magnum Spectrum. And so the first step was to calculate Magnum Spectrum of iridium. So iridium orders in, all out. We are pretty confident, and so magnetic band structure of all in, all out order will have this degeneracies, or there are three degenerate bands at higher frequencies and the one degenerate at low frequencies. And then what they did, they wrote this Hamiltonian, which includes all possible interactions between iridium atoms. And basically the value, they use the value which will fit our experimental spectrum. And so here are the value, and then from geometry of this order, they could predict polarization dependence. So this is parallel, this perpendicular polarization. And so the intensities agree in a reasonable way. We have the high frequency band, which is a little high because the additional intensity comes from the fact that it's a degenerate band. So basically, the first step is done. We, from our spectra, we know where the 1 Magnum excitations of iridium sublattice, and we got these values for the interaction between iridiums. And so the next thing is, and that took us a lot of time to figure out what it is, we have this very strong excitation which comes up at the temperature where iridium orders, but then so iridium order just doesn't change down to low temperatures, but this excitation changes dramatically as we cool down, so it broadens and it shifts high frequency, so it's like anti-soft mode, because like typically, right, for like there were a few like various discussions what it could be, like, okay, it could be sublattice soft mode. No, it cannot be, because if it's a soft mode, then it goes down in frequency and broadens. This one goes up in frequency and broadens. So then we thought, okay, what is left? There are no phonons. There is iridium excitations already there, so we can look and see what's going on with neodymium sublattice. And the first thing to think about is it could be a crystal field excitation of neodymium, which somehow is dramatically enhanced. And the answer is no. So neodymium, both neodymium iridate, actually crystal field excitations were measured with a very low resolution by neutron scattering. It has the same symmetry of the site and very similar environment like neodymium zirconate, so it was actually just additional thing to compare. We observe the crystal field excitations Raman scattering, and here I would like to advertise it. So a lot of times it's done with neutron scattering, but Raman scattering is the cheapest way to measure crystal field excitations in insulating systems. So we observe this the transition between the ground state and the first excited state. We agree here with neutron scattering down to a couple of milli-electron volts. It's at 25 millieV. So we observe it above, well above the temperature of the magnetic transition in neodymium iridate, and then it overlaps with Magnum's Magnum band of iridium. So here you see this ring, and in kind of just measuring neodymium zirconate was confirming that yes, that's the crystal field transition, and that's how it looks like. So this band, which is this kind of very strange excitation, cannot be explained by crystal fields. So then the next thing, and here I think like I have to always credit Natasha for all these ideas, that we started with the thinking, okay, what else can happen with neodymium sublattice? And neodymium sublattice is, right, so it's, the strange thing is that it orders at much higher temperatures than any ordering in rare earth systems. And for again, like neodymium zirconate orders at all in, all out at 0.5 K. Oh, sorry, 0.25 K. And there were actual couple of papers which, before we started, it suggested that what happens that iridium is the magnetic field from iridium moments basically leads to this crossover into neodymium in neodymium moments, and eventually they follow the iridium lattice. So what alternative way to look at it, which Nata suggested, was to look at how presence of extended orbitals of iridium, which actually enhance the interaction between neodymium moments. Because there is like many pathways where the exchange interaction doesn't go from neodymium, oxygen, neodymium to neodymium, oxygen, iridium, and back to neodymium. And there are many of these pathways. And so kind of we thought, okay, that could be kind of, we could think that there is some enhanced interactions between neodymium atoms, and that's kind of leads to some special behavior of the system. And what could be the special behavior? So the system is ordering in, all out at lower temperatures, but above there could be fluctuations of the state. Now, we observe a very strong collective mode, but it is all in, all out fluctuations wouldn't produce such a mode. But two in, two out, so quantum spin-ice fluctuations would produce a very strong Raman response. And again, Natasha's group had a paper long ago predicting a strong response of quantum spin-ice, and neodymium zirconate actually one of the systems where we should look for it, but because everything is happening at very low temperatures, which are very technically challenging for Raman scattering, we haven't got there. So yeah, so indeed neodymium zirconate is some kind of analogy. Because it does order in, all out at a quarter of Kelvin, but it does have two in, two out fluctuations above when it's out of the state. So basically, we decided to be very bold and assume that what we see is the response of kind of analogical to quantum spin-ice. And Natasha and Yang, they basically took a Hamiltonian, which would produce a quantum spin-ice, and did some fitting to our spectra. So if they take these parameters, which are pretty high interactions, then they reproduce the mode which we get in Raman scattering. So to argue I would like to argue that from an experiment that actually makes a lot of sense, is because basically this mode is very sensitive, right, to the what we know from other measurements, like even specific heat, development of all in, all out correlations between neodymium moments. So the lower we go in temperature, so this mode appears when iridium is ordering, and then as soon as we start to develop all in, all out correlations between neodymium, it changes, it shifts to high frequencies, broadens, low intensity, and basically disappears. So yeah, so this mode, right, so what comes out of this model is that this mode is basically a collective mode from spin-on continuum in this quantum spin-ice. And then as soon as we start to get correlations between all in, all out correlations between neodymium spin, it basically the coherence gets pulled and it disappears. So yeah, so how it disappears and why, right? So we know from previous proposal that there is this local field which is produced by iridium sublattice, and we kind of the suggested view on it that it starts to be more and more increasingly important as we cool down. This basically our approach agrees with that, and that was basically what makes it eventually neodymium to order in, all out state and kills this spin-on response of neodymium moments. So then kind of how we listen the ordered states there, Jeremy here in Geneva got a little bit lower temperatures than we could, even though like without polarization dependence. So we observe that this mode disappears, but then this mode, like there is another excitation which appears at very low frequencies at 30 millieV, and then so kind of it's logical to think that this is magnetic excitation from all in, all out order of neodymiums. And then again, Natasha and Yang did more calculations, what would be magnetic spectrum for neodymium all in, all out. And if they take the same parameters and then the previous Hamiltonian and add this local field, yeah, then they reproduce the mode which we have here, right? So it's again a fit, but in a way it's a restricted fit because the first set of parameters kind of agrees with both states. So Yeah, so what we think that we observe is that we observe, like in terms of magnetic excitations and what happens with these magnetic sublattices. So we do observe crystal field of neodymium at temperatures when no magnetic order is there. And then below 33K, we observe Magnum response of iridium sublattice, which is ordered in all out. And then just below this ordering of iridium, we start to observe the spin-on response of 2-into-out fluctuations of neodymium sublattice, which then eventually kind of decreases as we get the all in all out correlations in neodymium sublattice and disappears below the transition, and instead we observe 2 Magnum excitation of neodymium. So very shortly, because I saw the 5 minutes warning, I wanted to mention the electronic structure, right? So we started this all because we wanted to distinguish between quadratic band touching and while semi-metal, and see if we can do it with Raman. So Predrag Nikolic calculated for us how the Raman response of quadratic band touching versus while semi-metal will look like. And in while semi-metal, so in basically these interband transitions with linear dispersion, the Raman response will be quadratic on frequency. With some, so if we have a chemical potential, then we have some cutoff. If we get some kind of impurity scattering, then this cutoff will be washed out. So, and it can be very easily distinguished from the quadratic band touching, or like transition between quadratic bands, because those are expected to have the square root of frequency dependence. And so we kind of polarization dependence of Raman really helped us, because in the cross polarization, we completely get rid of these strong modes from neodymium sublattice, because it's A1G symmetry. And so we observe electronic continuum here on top of, like, with some the phonons and magnons on top. But this interesting in this part, which this electronic continuum actually changes as a step when we go from high temperature regime into the regime where iridium moments are ordered. And so then we looked at this and we fit it with what kind of basically functions for this electronic continuum. So we wanted to be very, very honest, and we checked if the continuum at higher frequencies, higher temperatures, could be explained by charge carriers, just quasi-free charge carriers. This is something which is known well. So it actually kind of very close to what we'll get from quadratic band touching, but then the parameters which we'll get, so it would be very, very large scattering for the quasi-particles. Metallic quasi-particles would be not in agreement with anything else which is known about these parachlors. So like a couple of orders of magnitude higher. So that kind of, then basically for us it looks like the square root, so this red spectrum, which is a high temperature spectrum, square root of frequency and quadratic band touching in agreement with what we see. So the temperature dependence of the frequency dependence of the continuum below the transition is very well fit by square the quadratic dependence on frequency. So from this experiment, we argued that we actually see the transition from quadratic band touching into this while modes, and it happens on the order of iridium. Yeah. Okay. So we kind of, yes. 1 minute. That's very, so Raman scattering measures phonons. That means that we see the response of the lattice, and actually in most of the magnets we're looking at, we always see that something is a little bit happening with the lattice. So it basically looking at frequencies of even gamma point phonons a lot of times is we see smaller frequencies, smaller changes than X-ray XRD could observe, and we can discuss why. So we actually see pretty kind of unexpectedly pretty strong response of the lattice. There was supposed to be no structural transitions. All this changes on the lattice, so this is like 3 phonons, which are oxygen phonons, they're continuous, so there is no sharp phase transition. And we still kind of a little bit thinking about it. So basically, the first triply degenerate and doubly degenerate phonons are broadening as we introduce the iridium order, and the EG splits as like really into bands as neodymium order kicked in. It is kind of, in principle, this would be in agreement with lowering of the symmetry of the lattice from just, if you look at the symmetry of the phonons from point group OH to D4H. So there could be some symmetry element lost. It is so weirdly, triply degenerate phonons are much less changing than this doubly degenerate phonon, but it looks like it also could be the question of magnetic-elastic coupling coefficient. This is the same as observed in European iridate, and so, but this is kind of under discussion. And so so just conclusions is that from a magnetic point of view, we observe the response of these 2 sublattices, and the most exotic thing which now propose that neodymium in this very narrow temperature range produces this spin-on continuum behaving like a quantum spin-ice due to enhanced interactions through iridium. And then we also observe an electronic scattering. We observe the evidence of this transition between quadratic band watching into wall nodes. Okay, thank you for your attention.
Questions?
So how large is the chemical potential mu that you observe?
So we it's below what we see. So we so okay. Let me actually. So so okay. No, it's not below. It's 8. Okay, it's cut here. Sorry, it's 8 millivolts.
Oh, I see. But then you can have the temperature larger than this chemical potential, and that there are very specific predictions for, say, the temperature dependency of conductivity for both Wildson metal and parabolic touching that one could test. Have you performed any transport measurements?
So transport measurements have been published for this material, which we could look at. So I mean, for this crystal even. So we could, and as far as I understand, they do agree. So, but I have to say that it's a nice thing to check, actually. Right. So there is also, I mean, to be honest, there is a little bit of the thing that it looks like, and this is something which I would like to understand, so I'm very honest here, because we see this cutoff of chemical potential in this low frequency, the low temperature regime. So we don't see this cutoff of the chemical potential at high temperature regime where we have quadratic band touching. So kind of, I actually, at this point, thinking if it could be basically that the splitting doesn't happen like exactly, you know, at the level of chemical potential, or we are not sensitive to it. There are 2 things.
Right, my point is that there should be very, see, for a while some metal, you should see T to the 4 in conductivity.
So we will, thank you, we will check it. I mean, as to quadratic band touching regime, maybe that will open your, answer your question. There is evidence for photo emission, which looked pretty kind of, made us confident that there could be quadratic band touching, right? And then there is, so for praseodymium iridate, which has very similar spectrum, there is a paper from Peter Armitage where they basically get it from epsilon infinity. But yes, it's interesting to check conductivity.
So thank you, Natalia. I have a question on when you are discussing the coupling to the lattice, and you were showing and you're saying whether maybe you have some structural distortions. I would expect, so it's, I think it was one of the slides just at the very end. Mm-hmm. Right. Mm-hmm. So when you're talking about you could maybe observing lowering of the symmetry, mm-hmm. I would expect if you do have that, you should see splittings, and I don't see any splitting. How can you then?
This one.
So this you call it, so going from, okay, so this is for your split, okay.
Right. So it's, so basically, we do, you know, like, it's a very practical thing, right? So if you have a double degenerate phonon and it broadens, right? So then, let's say you relieve the degeneracy. The question is amplitude, and the amplitude, for my experience, unfortunately, there are no, I don't think there are any calculations. It could be so small that we wanted to be expert of XRD. So it would be interesting, all kind of, to have some DFT, for example, we will predict
I'm more used to that.
The amplitude.
For instance, the iron-based superconductors, you see very nicely the splittings. And that's why you go to really low temperatures, you go to 7 Kelvin. Yeah. So I would have expected a more clear splitting there, but okay.
But you think about the like structural phase transition, right? And so there, it's not structural phase transition, kind of very intuitively, right? Not based on any DFT or anything. I see that it follows the crossover behavior of
so you think about some kind of
and I think that there is, like, as neodymium's order as a crossover, there is some kind of crossover like distortion of the lattice with really, really small amplitude. Right, because there is no other methods actually observe this structural change, but we do see that something. But we see the response of the lattice.
But for instance, PDF, right? In PDF, you could see indeed whether you see some changing of your
then
bonds.
The question if they can do PDF on this neodymium, there is So I mean, this is the whole sea of experimental issues with these particular materials. That's neodymium,
Okay, but
they could be. I mean, yes, it could be also dynamic because of this broadening.
Rosa, the splitting is there on the other plot. See, that's the splitting.
But yes, in principle, it could be slow dynamic, and that's why XRD. Well, XRD is higher frequent time scale, so it should actually see it still. I think they issue the amplitude.
Okay, I had a different question about the about this kind of exchange model that you have for the neodymiums. Mm-hmm. Did I see it right that maybe you can go somewhere where it was? So that you have an antiferromagnetic exchange between the neodymiums of order 13 millivolts, which is a huge energy. And I mean, well above the temperature of the metal insulator transition in these materials as well, right?
Yes.
So.
Yeah, I see your issue.
Well, I don't know. So in a magnetic insulator, mm-hmm. you would see the magnetic entropy, et cetera, kind of being partially quenched at some pretty high temperature. Are there measurements that it would mean that above this whatever 35 Kelvin, 40 Kelvin transition, the neodymium are not free moments, right? So is there evidence for that?
So there is. Neodymium has a lot of experimental issues, and now, like, kind of after I looked at this, right? So there are kind of, now I know, let's say, where to look at, right? Because there is some papers, especially early ones, there was, as soon as it becomes stoichiometric, it becomes very metallic. And so there is a paper from Nd2Ir2O7 and company, there's a peer B from a few years ago, where they observed magnetic susceptibility, basically kind of very tiny splitting between zero field and field at pretty high temperatures, like 100, which I never believed before, but now I think we should look back to it. So basically, in a way, I would say that, yes, there is this, we suggest this very high energy scale, and then we have to make more crystals, which we're doing now from experimental point of view, and look at this high energy scale, right? So it's basically this, I would say that the argument pro is that it's a frustrated system, and we see ordering of neodymiums at high temperatures, right? It's also, I would say that our imagination, we run out of
the ordering you see is opposite to the ordering of your exchange,
which comes with this, But so there is a little bit of experimental evidence, and I think we have to look for more.
Could it be that she has competing exchanges that she hasn't taken into account?
I don't know. I mean, the model has as written, is very much a competition between this exchange you have and the neodymium iridium exchange.
I mean, it's also actually semi-metal, right? So there could be like these interactions. It was at this point too complex to put this all in, so it could be some interaction due to the fact that it's a semi-metal.
Thank you. I had another question about I don't quite understand why you've chosen 14 Kelvin as the crossover temperature for neodymium ordering. It's well above this broad peak that you show in the specific heat. It's already a high we already discussed the high energy scale of the disappearing excitation, but this is already a high temperature scale compared to this broad peak in the specific heat.
So, okay, if I understand you right, so why we chose this particular, right? So
below it, there's a broad peak in the specific heat that's at 1 or 2 Kelvin.
Right. So we chose it as an upturn of the specific heat for this particular sample. And there is multiple evidence that this peak itself is due to this crossover ordering of neodymium in all in, all out. And as we actually, so 14 Kelvin is for this particular sample. If you look at literature, it a little bit varies, and it varies because in stoichiometric samples, it actually gets a little lower. So the highest temperature I've seen in literature was 15, but there is some lower temperatures, right? So there is specific heat compared here from Moiré. So our sample has 0.02 of stoichiometric. So of the completely stoichiometric sample, it also shifts a little bit high. I mean, we didn't get that temple.
I will quick.
No, it's so muons, because they cannot measure diffraction. I don't think they go so high in temperatures and diffraction, but okay. Like muons are very reliable, but muons also, there are 2 papers which are plus minus few K.
I'll briefly comment. So at 14 Kelvin, there is also this Magnum peak from the neodymium appears in the Raman spectrum. So that's where it starts to be visible in the Raman data. Okay, we need to go on. So last question, Wolfram, and then
just about the Raman, the magnetic Raman peak. So these are 2 Magnum excitations. Is that right?
Which one? There's 2 Magnum. Yes. So there are 2. There is one.
Not the spin-on one. Just the Magnum.
Yeah. I will go here. So
I can rephrase the question quickly. Are there bound states also? Or are these just bare 2 Magnum excitations? Does this model support bound states? Usually the quest for Raman, 2 Magnum Ramans in 2 Magnum Raman scattering is to find bound states.
Right. So these are 1 Magnum states. For iridium, we see only 1 Magnum.
This has 1 Magnum
yes,
states.
And the kind of, in fact, no iridates even ordered at high temperature C2 Magnum state. I suspect that the just they overlap with the electronic continuum.
So this is a non-Loudon Fleury.
So this is strong spin-orbit coupling.
This is just spin-orbit coupling.
Yeah, this is just spin-orbit coupling.
Thank you.
And the two magnons from iridium overlap with the phonon. So
no, it's actually even like kind of, it overlaps with the electronic continuum, I would say. So yeah.
Naive question. So for spin-on response that you find, how many spin-ons you couple to? So do you know if it's 2 or more?
Something more complicated. Right?
So
it's
the Raman operator coupling to spin-ons in that language. What is the coupling to? How many spin-ons you couple? How many spin-ons?
The Raman operator will be 2 spin, each spin, spin-ons.
Yeah.
So it's 4.
For 4 spin-ons.
Okay, so.
Yeah.
Okay, we need to continue. Thanks a lot for your talk.
Thank you.